besser. Magnetic guys want to go back.
So, good afternoon, PCS members and friends. Today we have a seminar, and our scientific host today is Professor Sergey Flach, who will introduce our speaker.
Okay, welcome everyone. It's a great pleasure to host two seminars today. I would call this seminar day the New Zealand seminar day because we have two speakers from New Zealand, and we have two talks, one now and one at 4 p.m. Please don't miss the second one as well. The first one will be given by Dr. Elke Pahl. Let me tell you a few words about Elke. She did her, where is it? Yes, here. So she did her undergrad and diploma in chemistry at the University of Heidelberg. And then she did her PhD in theoretical chemistry, again at the University in Heidelberg. And then she moved on with postdoc positions, first in the same place in Heidelberg and then in Seattle in the University of Washington. And then she moved back to Germany to the Max Planck Institute for the physics of complex systems, which is, I guess, where we met for the first time. And then she moved from there on to Massey University in Albany, first as a postdoc fellow, then as a senior lecturer. Albany, close to Auckland in New Zealand, I should say. And then she stayed in New Zealand, but switched universities to the University of Auckland, where she is still since as a senior lecturer in physics, although she's a theoretical chemist, which tells you that she knows physics as well. And she in particular also has lots of experience in, for instance, such more physics-oriented topics as phase transitions, Monte Carlo simulations, but also materials under extreme conditions, which is probably more getting back to chemistry, but again, nanoscience and electronic structure calculations and so on. And has a number of distinctions also, which maybe I will not read now. And the topic is very short of the talk today, extreme matter with an S in between, whatever that means. So let's welcome our speaker.
Okay. Hello, everyone. Thanks for the introduction, Sergey, and this opportunity to give the talk. And actually, I think my title was a little bit longer on the poster. It also said something about alien melting behavior. And so this comes already closer to what I want to be talking about, namely mainly melting, or also some solid-solid phase transitions we find. And the extreme matters actually, so the extremes I want to talk about is very high pressure and very strong magnetic fields. And there you see these pictures come in here. This is a diamond anvil cell where you can generate really, really huge pressures. So we can actually do very huge pressures on Earth. And I will come back to that a little bit later. And this is actually kind of an artistic impression of a magnetic white dwarf. And that's where actually both things then come together, that we have a very high pressure and can have very strong magnetic fields as well. And so our aim is to actually understand a little bit better how noble gases actually behave in these conditions.
So that's a white dwarf.
This is
Where is the white dwarf? This little white point in the middle?
I don't know. I'd say it's.
And the outside, what is this cloud around it, or is this all the white dwarf?
I found it. I just found it when I looked for nice pictures, but I think it's more artistic.
And it doesn't work.
Okay, so yeah, I'll just start with introducing my students and the people who kind of worked on these projects. So there are different projects I'm working on, but so this project I'm working on is mainly, like the results I'm showing are mainly done by Diana here, you, and some also from Ray Hunter, both PhD students in my group. And yeah, in collaboration with other people here as well, the ones in black, in bold phase are the ones which are also working on these melting simulations and so on. And yeah, so with that, just start with these questions why we want to do computer simulations. Of course, it's clear, but For us, there are several things. So one thing is comparison with experiments. They give us, of course, a better understanding and insight into what's happening in the experiments. And we can also validate experiments, but also vice versa, we can actually validate our simulations with that, which becomes, of course, quite important if we want to go to extreme conditions where we actually don't have any experimental data, perhaps, in the end. So this is really, as I already told you, in high pressure physics, this is possible because we can actually do high pressure experiments in Earth lab. And so we can do comparisons there with our simulations. I will come back to that work a little bit later, where we did some high pressure melting of iron. But then, of course, the computer simulations then also allow us to peek into the unknown. So there's some things where experimentally it's not possible or still not possible, like these really strong magnetic fields, which we have in outer space. And then experimental impossible per se. So there, I have one example where we worked on the melting of mercury at some point, where we did calculations, where we did calculations once with relativistic effects, but then also excluding relativistic effects, and were able to show that actually mercury would not be liquid at room temperature if we would not have relativistic effects. So if we would have not relativistic effects, it would be a solid at room temperature. So, and yeah, so overview over my research. I really love random stuff. So and nanoclusters for this stuff, melting moments, which is a suite which you can get in New Zealand at least. I don't know if it exists here in Korea. And then extreme conditions, we can find very interesting extreme conditions also in New Zealand. This is from a place which is close to Rotorua, where you have a lot of thermal effects, and there you have boiling water coming out in these places. Yeah, so as was already mentioned, so I'm interested in phase transitions. So one thing is in clusters, in little nanoclusters, up to 1,000 atoms or so, and then also in the solid state. Also, so melting transitions and solid state transition, and then the whole thing under extreme conditions. And in order to do that, we need potential energy surfaces, which we get with ab initio methods normally, or we use density functional theory or something then built upon the machine learning potentials. And we are using Monte Carlo actually to do the thermodynamic exploration of these potential energy surfaces. I also have work on some total different topics. So one thing is the full configuration interaction Monte Carlo method. That's something which I'm actually doing in collaboration with Joachim, and he will talk a little bit more about that in the second talk. But what we can do there, we use that to actually find ground in low-lying excited states, and can do that for bosonic fermionic systems or mixed bosonic fermionic systems. And this is an example, but actually this picture is not very good resolution anymore. But yeah, Joachim will talk more about that, so I leave that out. And then a totally different, more applied thing is that we are doing some modeling of nonlinear electric properties under stretching of some elastomers, which are doped with small nanoclusters. And this is a simulation, a collaboration with Bioengineering Institute at Auckland. And here you see some typical piezoresistivity effects if you stretch these elastomers. And you get these nonlinear peaks here, which are quite interesting also. So we have developed several programming packages using the relatively modern computer language Julia. And so I have a parallel tempering Monte Carlo package here, and then another package to do some cluster structure analysis. And then we have the Remo package, which is for this full configuration interaction from Monte Carlo.
What means random integrators? What is the random standing for? If you go one step back, it's just for random integrators. I know what integrators are, but what means a random integrator?
Random means that we are using in the end a Monte Carlo method.
Okay.
Use random numbers. And it allowed us to actually get this nice name of Remo here, which is actually a tree in New Zealand. So I will start to give you a short overview or general insights into melting, and then go to the potential energy surfaces, how we compute them, characterize them, and then explore them, what's important sampling Monte Carlo. And then I will go to the examples of melting of noble gases, just under high pressure, then in strong magnetic fields, and then finally in the combination of both. So if we want to get a little bit of first insights into melting, it's actually good to just start here. If we are in an isobaric, isothermal ensemble, so we have constant particle number, constant pressure, constant temperature, then we have that at the coexistence between solid and liquid, we have that the Gibbs free energies of the two phases have to be the same, so Gs equals Gl. And if we write that out, we have here the enthalpy and here the entropy of our system in the solid and the liquid phase. And we can rearrange this equation to actually get an equation for the melting temperature. And this is then just the latent heat of melting, right, over the melt entropy. So in the end, we have, as it's clear, right, we can see very nicely here already this competition, which we always have between energy, material, and entropy. And if we then also look a little bit more closely at this latent heat of melting, right, the enthalpy is actually the difference in internal energy, but then we also have this term here, which is the pressure times the volume difference, right? Which will, of course, as you can already imagine, if we go under high pressure, this term can be quite important as well to just determine what's happening. So we have these three quantities which are changing the internal energy, volume, and entropy under melting. And normally, or always, the internal energy will always be positive, the change of that one. The change in melt entropy is also positive. What can happen is that if we have something which is melting and we have some structure remaining in the liquid, this melt entropy will be smaller than usual, and this can lead to increasing melting temperatures.
So may I ask you a question? This slide just here that just there's some comments that about that the statements that you use this Gibbs free energy. So this the equality quite general, or is there some situation or material you have in mind when you?
So this is general, and if you have a problem with constant pressure.
But you said also isothermal, but if you
Isothermal,
But what is the parameter you vary actually? Because you vary probably the temperature, right? And then you come to the melting temperature.
Yeah.
So what means isothermal in that sense?
In that sense that at this point of the we keep just sitting at this temperature.
So no free parameters. Would change what? The volume?
The volume. So the variables which are actually conjugate to them, right? We can change the volume and the entropy. But yeah, so if you're in this ensemble NPT, I don't know, NVT might be more familiar when we have the canonical ensemble. There it would be the internal energy, which is the same. So the difference to the canonical ensemble is exactly this term here in the end, which is the pressure volume term. So this is talking about these two quantities, and this quantity finally in the end, the volume effects. In general, you also have that the volume will increase, right, if you go from a solid to a liquid. But you know some examples like water, the famous example of water, that you can have the effect where delta V becomes smaller under melting. And there are two reasons this can happen. One is that you have a higher coordination number in the liquid phase, or that you actually have a decrease in the nearest neighbor distance in the liquid. And yeah, this famous example of water. And this is also something which we immediately see then from the Clausius-Clapeyron equation here, where we have the dependence of the melting temperature of the pressure, and we see that we can get a negative slope here when delta comes.
So if you can go one slide back, please. So what is the reason for the anomaly, the water anomaly? Is it?
This is the coordination number.
It's a coordination number, right?
Because you have this flake structure in the solid, which is actually not very dense, and so if that melts, you can get a larger coordination number. And this is actually, so you could also call that actually reentrant melting, but reentrant melting is actually something I come to in a minute, where you have normally, so for example, alkali metals, where you have the second thing as the reason. Yeah.
I have a more basic question. So what do you need to see in your simulation to say, oh, it is a liquid or it is a solid? Like what are you looking for?
Yeah. So you can define different order parameters for that, right? So there are order parameters out there like the Lindemann index, which looks at just the distance between the particles. But what we are using normally is the heat capacities, which gives you you have a clear jump at the.
Are you looking for a phase transition?
We're looking for phase transition.
But can it be some phase transition between like liquid and different liquid? Or, Wouldn't there be some phase transition between like some liquid or different liquid? I know you have some crystalline structure and different crystalline structure.
So we always have to, of course, sometimes we know that it can only be melting, but we, of course, in a peak in our heat capacity curves only tells us that we have phase transition. And then we have to look more closely into what's really happening. So what we are using for that normally is then, for example, radial distribution functions, or we do some look really at the configurations themselves, which are sampled, which then can tell you, especially the radial distribution function tells you clearly if you are still in a solid or in a liquid phase, because you will see in the liquid phase there is still a little bit of structure remaining, but normally it becomes quite washed out if you look at just which distances you have in your clusters, whatever you are simulating. If you're in the solid, you still have a very distinct.
Because you see the peaks, therefore you can infer that you have
Exactly.
structure.
Yeah.
Okay.
So
I will have some examples later.
Usually when you want to have a solid, you can get the density correlation. You see that it pick some vector.
Correlation.
Density correlation. You see that pick some vector is a lattice if it's set.
Yeah. So yeah, as I already just mentioned, right? So we had this example where we have water, where we have a negative coexistence line, but in principle that can also happen for other stuff. And an example here is, for example, sodium. If you put sodium under high pressure, so here you have the melting point in this direction and the pressure here. You can see that at the beginning, the normal thing happens, that what you would expect, that the melting temperature goes up if you're increasing the pressure. But then at some point you actually have a reverse and it's going down again. And it's changing. Here you have actually a solid-solid phase transition from BCC to FCC. And then it goes still further down here until it's actually even at 300 Kelvin here, at 100 gigapascals, it goes back to 300 Kelvin. And then
it melts already at 300 Kelvin.
Yeah.
Which
it's huge.
at least here bigger pressure.
And the reason for this is here that the distance between the atoms changes. And the reason for that, again, is that under high pressure, you can have really interesting effects. One thing, of course, is that nature always tries to minimize the volume because we have this pressure volume term, right? But this is not only going from here you have a BCC phase to an FCC phase, right? So that's something you would expect because you go from a less dense to a denser atmospheres. But then here you actually, if you look here, you get another phase transition here. And here you have a very strange phase, which has a much lower symmetry than before. And the reason behind all this is that under high pressure, S orbitals are actually much more impacted than P orbitals or D orbitals. And so you can have a reordering, an energetic reordering of these of the orbitals kind of, and so you can get totally different binding character. So,
In this case, the distance between atom and now is order of angstrom to see this effect.
this one?
The distance between two
Yeah.
atoms, order of angstrom to see.
Yeah,
this effect.
you can see this effect. For example, again, in radial distribution functions, you can see that.
I mean, how much does the average distance change if you go from ambient pressure to 100 gigapascal in the FCC? Is it this?
I don't know it here in this case for sodium, but I know it in argon, for example, you have a change of more than 10%.
10%, not so much,
Not so much.
but it's still a lot.
But it's still a lot, because if you think about it, you are moving up with help really strong repulsive wall.
Not that much.
Sorry, question, any directional dependence that matter, which direction you at this pressure?
This is actually all for hydrostatic pressure, so you have the same pressure from all sides. But actually, this will be important. So at the moment, we are all doing all our simulations are actually using hydrostatic pressure, but experimentalists who do these diamond anvil cells, they've also tried to get hydrostatic pressure in there. But this is a little bit questionable, and there might be some things where that becomes important. And yeah, so that's a future direction I want to go into, look more into also non-hydrostatic. Yeah. So now our melting simulations, in order to get the information which we need, right, which is the internal energy in the end piece, we need in the end the partition function, or we can start from there, right, from the partition function. And here we are doing classical simulations, so we use the classical partition function here, and so we just have to kind of integrate over the whole phase space in the end. So we have the momenta here, and then this is the spatial coordinates, and we integrate here over the volume, which will allow for our clusters or our simulation. And then here we just have our Boltzmann vectors, where we have the exponential of the energy, so the kinetic energy here and the potential energy here.
So what is the coordinate here? Is the coordinate of the atom?
This is now for our anatomic system, which we're looking at. So that would be the potential energy surface of this system we are looking at. And this is the kinetic energy. So N is the number of atoms.
But I thought that's when you push this like strong together, the electron become important, right?
Yeah, you will get the repulsion, energy repulsion of that. This is actually included in the potential surfaces. Yeah. So this is what you get if you solve the electronic Schrödinger equation. Yeah. Yeah. And so if you look more closely into that, so the nice thing here is what we have here in our Hamiltonian is that the kinetic energy and is only dependent on the momentum and the potential only on the spatial coordinates. So our integral actually here separates into two parts. And when we only look at the momentum part, we see that this is actually just the integral for an ideal gas. So that's the partition function of an ideal gas. And then we have the so-called configurational partition function, which is the integral over the spatial coordinates. And yeah, and then if you want to get the internal energy from there, right, we just get it by the derivative of the logarithm of the partition function. And so in the end, we get this sum here of two contributions, ideal gas contribution and configurational contribution. And so this one is the one which is of interest for us.
And how do you get the pressure into the game?
The pressure we get into, so this is now for the canonical ensemble. If you do the same thing for the isothermal isobaric ensemble, we will have another integral here over the volumes. So we also have to integrate over the volumes, and you can then do some transformations here in the integrals by scaling what's in here, so that you always scale over a unit volume. And if you do that, actually, it just actually is an addition of a pressure volume term, essentially. Here in this term.
Sorry, you showed before that relativistic effects can be important, and all this seems to be non-relativistic.
We could include scalar relativistic effects in the potential energy.
It's relativistic, so the P's are the momenta of the what? Of the atom?
But this is of the atoms now.
Right, and I think the relativistic part concerns the electrons.
Comes from the electrons.
But
That's
relativistic part will probably make energy dependent on not only positions but on velocities also.
It's the potential energy.
This is the momenta of the nuclei of
Nuclei.
the nuclei.
Okay.
Right. So this is what you get if you solve the electronic Schrödinger equation.
So somewhere there you have to go relativistic.
Yeah, and so there you can include, so if for our relativistic simulations for Mercury, right, that was included here in the potential energy. And for Mercury, actually, it's only the scalar relativistic effects which are.
Yeah.
Oh, okay. If you need on the scalar.
But otherwise, if we also included spin orbitals, but then you have to actually go to the Dirac equation.
Yes.
So where does the relativity come in? Is like electrons like fast or?
Electronic effects, relativistic effects become really important if you have very heavy atoms like Mercury. So in this row where you have Mercury, gold, and so on, you have all the relativistic effects. And the reason for that is that the nuclear number becomes so large, right? So that the electrons which are close to the nuclei also become really, really close, and you can show that you get relativistic speeds of about 10% of the speed of light for these electrons. And the interesting thing is, so Dirac actually thought it doesn't matter for chemistry because it's the valence electrons which do the chemistry. But it turns out that for these S electrons especially, you get strong scalar relativistic effects because they still have a really huge probability to be close to the nucleus as well.
So close
Also
means that this force, if it was like classical model,
yeah.
the force must be very large.
Yeah, exactly.
To like stay orbiting.
Yeah.
Right. And somehow it transfers to like orbitals which are not moving at all.
Exactly. And that's the effect of that in the end is that the S orbitals contract. So they become more stable. And this in the end leads to the fact that Mercury
there is some kind of like relativistic Schrödinger equation there, or where does it come in from?
That the electrons are close to the nucleus.
Yeah, like
I think the question is if you want to include these relativistic effects for the electrons, then what kind of equations do you use?
So there are two things. So the scalar relativistic effects are relatively easy to include because you can include them in the pseudo potentials which you are using. Right. So you can. So you just have to use so-called relativistic pseudo potentials for that.
Okay.
But if you want to include scalar relativistic, the spin orbit coupling, then you have to actually start from the Dirac equation, which you can transform to a two-component equation, and then you have to.
I see. So you can just modify the classical potential somehow with some relativistic effects.
Yes.
You want to do it like.
Yeah. So for Mercury, this is actually sufficient. So you can show that the spin orbit effects are not important for Mercury. It's just the contraction of the 1s electrons actually, which makes it. And a similar thing for gold, the golden color for gold is also a scalar relativistic effect. Okay, so just coming back to here, right? So we have our partition function, and from there we can actually get in the end the internal energy. And the most important thing here, because this is just a constant here, is the so-called configuration internal energy, which I have to find. And as we said, if we have also the pressure to be considered, or the pressure constant, then we have a pressure volume term here as well. So in the end, what we have to do is,
It will recover. No problem.
Can I ask a question?
Yeah.
So if you have this NPT ensemble, then shouldn't you also include the chemical potential?
Yes, so this would be really in the, as I said before, this is in the canonical ensemble where we have NVT, right? So we have two different kinds of simulations which we are doing. Some of them we are doing, if you have ambient pressure, right? We normally use the canonical ensemble where we have constant volume because it's easier. But if you want to, of course, have pressure effects, we have to include this pressure volume effect, pressure volume term, and this comes just in here. So you would just have the kinetic energy plus the potential energy plus P times V.
Not a chemical potential, I think, right? Because
No,
the particle
the
number.
particle number is still constant.
I see.
Yeah.
Ah, okay, then
Yeah.
that is the Fugazi.
Yeah. No, so we have a constant particle number, so that's why the chemical potential is. Yeah. And so, yeah, what we want to solve in the end or calculate is this configurational internal energy. And this is a 3n dimensional integral, which we still have to do. So quite high dimensional integral, which we in the end will do with Monte Carlo methods to use to solve that. Yeah, so this is our internal energy. So we can identify here this the potential energy surface of our system. We have this high dimensional integral, which we will do with Monte Carlo methods. And then finally, we have a probability function here, which is our Boltzmann distribution. And this probability function is quite handy because then it allows us to do important sampling really easily. So in the end, what we will be doing is important sampling, important Monte Carlo sampling. Yeah. So we will start with the potential energy surface now, and just I called it U-pot before, and now from now on I call it ENR, just to make also clear that it's actually depending on the number of particles. Yeah, and it's just giving us the potential energy of an n-particle system independent of the particle arrangement, also the nuclear arrangements. Which is, of course, this is a cartoon picture, but we, of course, the larger our system, the more minima we get, right? And the potential energy surface can get really, really complex on that. This would be a really easy one, which we sometimes have, where we have one very low-lying minimum and like a funnel going, everything goes in there. But actually what we often have is that we have several of these minima, which are also quite similar in energy and separated by large energy barriers.
So you're trying to find the minimum.
So we could also find the minimum, but this gives us just how the system would look in the equilibrium situation. But we also have to explore now to do thermodynamics, right? We have to explore the whole surface also at higher energies, right? So our integral in the end does that, right? Because we have here this integral over the potential energy. And then we have the Boltzmann factor, which tells you how important a certain region and phase space is. And this importance almost depends on the temperature where you are at, and then on the energy. Right? So the higher your energy, the more of the potential energy surface you will actually explore.
So how many particles you can in principle calculate using this method?
We went up to a little bit more than 1,000 atoms in one case. But these are then already calculations now, which take 3 weeks or so on the supercomputer in parallel. So it's very quickly becoming quite difficult for computational expenses.
Sorry. So if your potential energy surface, if it has many local minima,
Yeah.
then this integration will not be that accurate, right? In general.
If you have lots of minima, right, you can already see that because here only the energy goes in, so they will all be important, right? So they have the same importance.
You have to sample all of them.
You really have to sample everything, and this is really can be a problem, and I will tell you in a minute how we overcome that.
Okay.
How we make kind of sure that we really ergodically sample information space. Yeah. So I just start quickly. I don't tell you much, but that's how we, in the end, solve the electronic Schrödinger equation to get these potential energy surfaces. And we are using mainly coupled cluster methods for that. If it's a more difficult system, we are having to go to density functional theory, or even then, kind of based on density functional theory, you can develop machine learning potentials, which then allows you to get the potential energy surface for that. But for the noble gases, which I will be talking about here now, what we normally do is just a many-body expansion of our potential energy surface. So we expand the whole thing, which we have, into dimer interactions, and then we add trimer interactions, and then we hope that it's converged. And for noble gases, often for the lighter ones, especially helium and neon, it's normally enough to just take the dimer interactions and add them. And so this approach is adequate for weakly interacting systems where dispersive interactions only. So that's noble gases or molecular systems. And then we can actually then use, of course, expensive methods to calculate the dimer curves with coupled cluster. And then it is a little bit of interest for us also to characterize the surface, to know how many minima we have, and also how they lie to each other, right? How they are connected to each other with the transition states in between. And there are methods around to actually find all global and local minima, or lots of them at least. One method which we have been using is the so-called Bayesian hopping methods. We would just hop with really huge steps over the potential energy surface and always minimize at these states to find these minima. And then we characterize the minima to automatically kind of be able to assign a certain structure to these minima. For example, we can decide if it's an FCC structure or an icosahedral structure. And then we can make plots like this, for example. So we characterize kind of each bond in our configuration by something which is called common neighbor analysis, where you essentially assign 3 numbers to every bond in your cluster, which kind of describes the neighborhood of these bonds. So how many neighbors you have and how they are connected to each other. And then you have kind of fingerprints like that. So 3 numbers for every bond, and then you calculate, and then you can actually see that icosahedral structures will have a lot of 555 signatures here, and FCC structures others, and so on. And so you can automatically then also assign what kind of structure you have. And then we can use that.
When you're doing this, then, for example, if your system like happen to be in quasi-crystal, we will not find this, right?
Then you will not find it, right? Yeah, because
but how can you like modify your method so that you can even?
I could imagine that you still I think quasi-crystals should still be possible in principle, because it is a very local. You still have local symmetry, right? But the symmetry might change, right?
Yes.
So, but I would imagine if you know what kind of quasi-crystal symmetry you still have, you could still probably automatically find out with these. Yeah, perhaps you need more than one typical.
You need more than that.
More than that. But perhaps if you have 20% of these numbers, so you might be able to. But I don't know. But what we do here is that we select one cluster with a special symmetry, and then we compare kind of the other clusters to this structure, and can kind of introduce or a similarity score, and then we can kind of plot that against each other, and this allows us to kind of visualize the potential energy surface a little bit. So here we compared with an icosahedral structure, and then you get lots of icosahedral structures here in this region, which are very similar. So these are the red points. It's not easy to see, but these are all icosahedral structures here. Then here in this region, you would have actually some decahedral structures here. and here you would have FCC-like structures. So in that way, we can get a little bit of an overview, and we can then later use it, because in our Monte Carlo simulations, we kind of sample these configurations, right? We can use these methods again to actually see what kind of configurations we are sampling at the different temperatures.
However, in this way, you do not consider the entropy yet, right? The entropy.
The entropy is kind of included in the formula for the internal energy.
Okay. Right.
So now to Monte Carlo methods, and we are using the important sampling Monte Carlo method. And I don't know, are you familiar with this method? Probably, right? So there's a very simple explanation with this map of Egypt where you want to measure the river, the depth of the river Nile. And so and you can see that any grid method would do very badly here. But if you actually are already in the river Nile, and then you just do a step to the side and measure again, right? And then decide if you actually keep that step or go back. This is kind of what you do with the Monte Carlo method. And that is, of course, very similar to now our potential energy surface. And if you're already in one minima, right, we want to explore this minimum better. So we go a little bit further there, and then we decide on the energy difference which we get if we keep that or if we are going back to that. And this allows us, it's really ideally suited for this kind of integrals which we have here, right? Some energy here times the probability function. And now I come to the point where we talk about that we can have problems, right? Of course, to be stuck in minima at low temperatures, especially, so that we would explore this minimum really, really well, but we actually couldn't find the other minimum here, which is also important temperature, right? And it will be really, really hard with this method to actually go over this energy barrier. So what we are using here is something which is called parallel temperature intercalo, where we do several temperatures at the same time. And then occasionally we try an exchange of configurations between neighboring temperatures. And in that way, we are able to actually communicate kind of, if this high temperature finds new interesting parts of phase space, it's able to communicate it down to the lowest temperatures as well. And this works really, really well, very efficiently. And so you will see later we are able to actually go from FCC, for example, to HCP structures in a simulation mechanism. Yeah, and a nice thing which we also can get from our parallel tempering Monte Carlo simulations is something which is called the multi-histograms, where we in the end we just count how many configurations do we find at a certain energy and just make statistics of that. And so if you're at a very low temperature, it's a little bit hard to see, you get something which looks like that here, just one peak here. And if you go higher and higher in temperatures, these peaks become broader. And I can show it here as well. So here you just have the number of configurations that you're looking at. Here you will have the energy of your configuration. So at a very low temperature, you just get a peak like that. If you go to higher temperatures, it becomes broader and broader, like this. And at some point, you will start to get a second point here, and this gets. And this is actually very typical for phase transitions, especially for the melting transition rate. By the way, you're suddenly able to kind of sample much more configurations at a higher temperature because it's so many, this entropy factor which comes in. Yeah. And a nice thing about this, storing this data, is actually also giving us access to the density of states. And this actually allows us then in post-processing step to actually calculate the partition function itself. And from there also find all the other information we might be interested in, for example, the entropy as well. And we can get very nice heat capacity curves from there, which are very smooth then. Here's a typical thing which we can get. Now here we are in an NPT ensemble, right? So the pressure ensemble. So we have the volume as well as a parameter here. So we have here the energy and the volume here. So these diagrams which I have shown you here become three-dimensional, right? And so here we can see kind of these peaks now, which are kind of moving in this direction to higher energies and higher volumes. And then at some point you see this phase transition happening. So this is moving along this curve, and then we have the phase transition. So this is 32 neon atoms in this periodic boundary conditions in this case. Yeah, so just a little bit more detail. So we use this important set of Monte Carlo, which means we place our atoms randomly in each step, or alternatively, we do a random scaling of the system to change the volume for the NPT ensemble. And then we accept or reject the new configurations according to our Metropolis condition. And then this allows us in the end to get the thermodynamic properties. If you would have an infinite system, of course, for such a first order phase transition, right, you get a jump in the internal energy and the entropy at the phase transition, and you get the heat capacity here. We have this jump here, and then you will see that if you have a finite size system, all these transitions will be just a little bit smeared out, right? So instead of this, for the heat capacity, we get a peak in the heat capacity here.
You mean that there is a coexistence in that region, right?
Yeah. So, and this also, in the end, if we do our nanocluster simulations, which are of course quite finite systems, right? This allows us actually to define melting, that we can just say our melting temperature is just a peak in the heat capacity curve. And for our clusters, we are using spherical boundary conditions, where we just put it into a sphere and don't allow the atoms to move out of this sphere in order to suppress atom loss processes, because these clusters would not be stable like that. And alternatively, we use periodic boundary conditions, just have a cell which we simulate. So in the end, we have different possibilities working in the NBT ensemble. For clusters, we normally use these spherical boundary conditions, or we can use the infinite system here with periodic boundary conditions, which works well for NBT and NPT ensemble. Here we actually have a problem because it's a really hard problem, or problem which is actually, I think, impossible to solve really, is how we define a volume of a cluster. So this is not clear. But the nice thing is, in principle, if you have kind of, if we do clusters and we make the clusters larger and larger and get the melting temperatures, we can actually extrapolate to the infinite system as well. And this is just an example here, still without extremes, right? No magnetic field, ambient pressure. You can see here some heat capacity curves for argon. You see a 13 atom cluster, which is quite intriguing that a 13 atom cluster already shows something like melting, right? Just 13 atoms together, but you get this very broad heat capacity peak. And then if you go up, you see how these melting peaks become more and more defined. And then actually from here onwards, from these clusters onwards, we can actually use the melting temperatures and plot them. If you plot them against the inverse, and against the volume in the end, so the inverse number of particles to the minus 1/3, you see that they all start to lie on a line. This allows for extrapolation, and then we actually get very close to the experimental melting temperatures here in this case. So this is for neon here, where the experimental melting temperature is here, and what we get from our extrapolations, we get here. And it turns out, of course, for neon at ambient pressure, there are already quantum effects which can become important. So with our classical simulations, we do some errors here. So this is actually the difference here can be attributed to quantum effects. And here in this case, for argon, it's the free body effects. If we neglect the free body effects, they become a little bit off as well. But in total, we get very good this experimental data. So it just shows us that this method works quite well.
Sorry, here this data,
Yeah.
y-axis, this is the distance between
Yeah.
what?
The inverse.
Okay. Here,
Yes.
yeah, this is the inverse, so the number of atoms to the power of minus 1/3, which is in the end the inverse of the volume of the cluster.
No, or the inverse of the linear scale. So the volume is the cube of this.
Yeah, the cube of this, yeah. So, yeah, so you can show that this is also the case for other systems. So you don't have these, not only for weak-phase systems, that was shown also experimentally for whole clusters, for example. It's only the spherical nature of it that you need, kind of. So that works.
So I wonder, because you said it corresponds with the experiment, but then can it predict also the systems when we don't have experimental data? Because if you show just noble gases, right, can it predict something that's not a noble gas?
Yeah, I'm pretty sure that it can, right? So, but in order to check our method, right, we wanted to make sure that we get the experimental melting temperatures out for this infinite system. So we don't have any experimental data yet for the clusters, for example. For these small clusters, there are no experimental data on melting temperatures of argon clusters. So that would be a prediction.
Oh, so that part is the prediction.
Yeah, so this part is something we can't actually compare to experiments, because experiments are not able to actually kind of, they would have to stabilize these argon clusters in a matrix probably and make them, yeah. But then also to get clusters which exactly have 55 atoms is really, really difficult.
Could this be applied, let's say, in like accelerators, when you have these like weird spaces of matter, when you hit against each other some atoms? Probably not.
Don't think so.
Okay.
Okay, so now I'm coming to the first part of applications, which is the high pressure melting now. And here just some typical pressures which we have: atmospheric pressure 10 to the power of 5. And then the interesting pressures kind of start here in this region where you have 8 gigapascals of pressure. So million times of atmospheric pressure in this region. So the oxygen becomes suddenly red, and it has actually all 8 molecules which are coming together, and they're these squares, kind of double squares. They look like that. And at 100 gigapascal, for example, oxygen becomes also metallic. Then. And that's happening to every metal. It will happen at some point. To every substance, it will become metallic at some point. And here we are also very close to the pressures which we actually have at the Earth. And the nice thing is, as I already told you before, that we have these diamond emerald cells where you can actually get these huge pressures very easily by just having very small cells here, right, which you put under high pressures as the diamond emerald cells. Yeah, and yeah.
So in this 100 gigapascal, not 100, 10 gigapascal, when oxygen becomes O8, what kind of phase transition is that?
This is, so you would have, in the gas, you have an O2 molecule normally, right? And then if you solidify it, it will still be O2 molecules, but kind of coordinated together. But yeah, you will have a phase transition, solid phase transition at some point to these ones. And what's at work here is actually, again, this minimizing the volume.
Right. It's would it be a structural phase transition?
It's a structural phase transition, yeah, and they have shown that. This comes from experiments. So they have done these experiments where they have found
in the solid phase.
In the solid phase, yeah.
Not in the gaseous phase.
No, in the solid phase. Yeah, and they will arrange like that in the solid phase. Yeah, just an example, right? Ice melts at 10 gigapascals. Ice would actually melt at 400 degrees Celsius. If you're now going to argon, and this is actually argon here, solid argon, the melting point is around 83 Kelvin at ambient pressure, and it goes to 1000 degrees Celsius at 10 gigapascals. So it has a much much stronger increase under pressure. And here we actually have some simulations where we melted argon under high pressure. This work was done by a postdoc in our group. Time, Jonas, you might still know him, I'm not sure. Yeah, but yeah, what we get here is that we actually get, again, very good agreement now with experimental results here as well. We have diamond annual cells, which can do that. And you see the experimental data here as the points. And here's just an insert to show how good it is between 0 and 10 gigapascals only. And then if you go up, you see that up to 50 gigapascals, they actually have a very good agreement with experimental data. And then all the theoretical predictions until now go up like this, whereas the experimental values suddenly start to curve over. And we don't have any good explanation for that yet. We tried already lots of things, but also in our simulations. But my suspicion is, and also from some experimentalists I talked to, is that we actually get into a regime where the hydrostatic approximation or assumption is not valid anymore. So we might have actually non-hydrostatic pressure. Yeah.
Can you change your potential yield to capture the high pressure?
To capture the non-hydrostatic pressure, it will be a little bit difficult. We don't know yet, but yeah, we might be able to actually have capture it by having different pressure in the different directions. So scale the volume differently in the different directions. But yeah, I have to test that, so we haven't done it yet. Yeah.
What do you mean by non-hydrostatic?
So that the pressure applied is not the same like from all sides. So they try a lot in these annual cells. Of course, you apply the pressure over the diamonds, right? Putting it together. So you have to somehow distribute the pressure so that it's really isotropic. So they have these little cells where they have normally, I think, tungsten rings, where they have the little sample inside. And normally they also put some noble gas actually in there, normally, to distribute the pressure nicely. But then here for argon, they actually used argon itself and say that that's kind of the medium which kind of distributes the pressure. But then the argon itself becomes solid. So I'm not totally sure how they can actually, they can be sure that it's the hydrostatic in these cases. So yeah, I guess that might be a good, at least it's a possible explanation. So, but we're still looking into it also from computational aspects. Yeah. And here now is for argon, neon, and helium. So you see also helium is actually getting to pretty high temperatures, melting temperatures. Here at 100 gigapascals, we are around 1000 Kelvin now. And this is also in agreement again with experimental data here. So I think, yeah, so high pressure we can handle quite well, at least if it's hydrostatic. Now,
okay. There was a problem with Microsoft PowerPoint. Maybe you want to get the laptop.
Yes, you should.
We cover work and
can I start again? Yeah.
I think so. From the very beginning.
oh, yeah, something is wrong with this slide. Maybe they're trying to make one.
Yeah, exactly. Was not a very interesting slide.
Maybe there is a bug in this. Maybe it's because the 1 hour is over. Okay.
Oh, is it?
Okay, this works. Okay, good.
But this works now. So now.
We already saw it.
So I will try to. No, we are still in.
That's we have it.
I try to go through.
Yeah.
I hope it's.
No.
Yeah, no, I should go other way.
That's a hard cutoff.
So it's a cutoff in the number of slides. What is it? This is our laptop?
Yes,
My laptop.
No, and it's your PowerPoint file?
Yeah.
Okay.
That's broken probably.
Just don't use the full screen, no?
Yeah, just don't use the full screen.
Okay.
That's a good idea. Why did that happen? Something is there which is not scalable. probably.
First time it's broken.
Scaling doesn't work all the time. Where is it?
I try one more thing
No.
to skip this one slide.
Okay, let's see what will happen.
No,
No. Something is wrong there.
it's really strange. Because
In
it was
compa-
working on my computer.
Yeah, sure, it's because
Yeah.
you're,
But yeah, then I do the other thing.
you also have a Mac, right, I guess?
Yeah,
That's okay, just leave it like this, it's big enough.
like this is fine, yeah.
But you cannot switch now, oh, can you? Can you?
No.
Whoops, no, you probably have,
Then I have to go here,
you have to do it manually.
so I get some. Let's go to. Okay, so from here. So it's just some typical magnetic field strengths you can find on Earth. And the thing is, like 10 Teslas is normally considered a pretty high magnetic field, but what you find in the MRI machines. And you have diamagnetic levitation there. These are these videos you might have seen that it can levitate Fox and these magnetic fields. And then, but if we go to higher, if we want higher magnetic fields, we have to go out in outer space. And there we have these magnetic white holes where you can actually find magnetic field strengths which are between 3 Tesla and 10 to the power of 5 Tesla. And this is actually the region where I'm interested in, because what's happening here is that the magnetic forces and the Coulomb forces become comparable with each other. And that, of course, means that we also get some interesting chemistry happening because we have competition between magnetic and electrostatic effects. So, and then, of course, you can have even larger magnetic fields in neutron stars and magnetize.
But I guess that in this situation, what to become very important, your classical simulation when you lose a game.
We would hope that it still works, and actually, it might actually work. In these situations here, it might still work even better, because magnetic fields introduce confinement potentials via the diamagnetic effects. And that might be the case, like with high pressure as well, that actually the classical approximation becomes better again. But these are all things which are not totally clear yet.
Neutron star.
Neutron stars, yes, but in neutron stars you have already such large magnetic fields that the electrostatic forces are neglected.
So my point is that the Pauli principle will be very important for neutron star.
Mm-hmm. Yeah, but I'm not talking about neutron stars magnetic fields. I'm talking about those where you have the magnitude so that the magnetic forces and Coulomb forces are similar to each other. So here in these cases, neutron stars magnetize you in the so-called Landau regime, where you actually have to treat it very differently the magnetic fields. And atoms as such stop to exist actually, because you will have plasmas. So we are interested in this intermediate regime between the Coulomb regime and the Landau regime. And so in this regime, you can normally always treat magnetic fields you have as perturbation only, but here we actually have to treat it differently. And then here you have the magnetic interactions becoming dominant. The interesting thing about this regime, as I said, right, you get this same orders of magnitude here, and that means actually that your atoms become ellipsoidal now in magnetic fields. This is the magnetic field Hamiltonian, so where you have the orbital Zeeman effect, the spin Zeeman effect, and the diamagnetic term. And here you can see that this term will always be positive, and this is this confinement effect we talked about. For noble gases, this term will always be 0, because we don't have any spin, unpaired electrons. And this is most of the time 0, but not always, and that will become very important in a minute. Whereas the diamagnetic effects, as you can see, they will always be positive, so always destabilizing our orbitals, so they will always increase in energy. Whereas these two effects can be positive or negative. So we are still doing our many body expansion, but what we are getting now is actually, which is good for weakly interacting systems, but we get a new effect, and this is the so-called perpendicular paramagnetic bonding. And I just quickly explain it like this. In a very simple picture in this LCAO picture, linear combination of atomic orbitals. If you have two 1s orbitals, right, which are both full and they come together, you build the binding and anti-binding orbitals, right? And in the case of helium, both of these will be filled, and that's why you would get no net binding here in these cases. And that's why you only have, you can have bound helium dimers, but just because of these very weak dispersive forces, and a helium dimer is really, really huge as well. It has actually 52 angstroms. Yeah, large. And it's so flat, the whole potential curve, that you can't even fit an extra vibrational level in there. And that's also the reason that a solid would not be bound at ambient pressure. So you need pressure to actually get helium solid. But not now what's happening in magnetic fields. We actually have this term here. And it starts to become dependent on the orientation of our molecule with respect to the magnetic field axis. If the magnetic field axis in this direction and the molecular axis is in the same direction, we have still total symmetry, and this term will still be zero. But if the molecule rotates away from that, it actually starts to break symmetry, and this has an effect actually on the anti-binding orbital only, not on this one, because this is totally symmetric. So this term will actually lead to stabilization of this orbital here, but not of this one. And now you get an energetic lowering of this orbital, right? So in the end, it means you get a net binding from here. And this is what's called perpendicular paramagnetic bonding, which you have here in this case. So this orbital is lowered so that this anti-binding is smaller than the binding. And so this gives you a net bonding in these cases. So this is called perpendicular paramagnetic bonding because it's, of course, the strongest if the molecule is perpendicular to the axis. And here you can see that in potential energy curves, if we calculate it, independence of the angle, right? You can see that you go down in energy here, and also the distance between the atoms becomes much closer. So this is for helium, and this is for neon. For 0.3 atomic units, which is 0.3 times the 230,000 I showed you before, so around 10 to the power of 5 Tesla. At these points, the singlet state of neon is still the constant. And if you do melting now, I hurry up a little bit. You actually, what you get, because you have now a stabilization, you get actually all your melting temperatures go actually up, increase a lot. And if we do the same as before and do these extrapolations of our cluster results, we actually find that we get an increase in melting temperature. So this is here for neon clusters, and this would be without magnetic field. And then this one here is a magnetic field of 0.1 atomic units. And then here we have the 0.3 atomic units, which is the red line here.
Can you do something more fun, like you put magnetic field from zero from the beginning?
Sorry?
Let do the fun game. You make magnetic field zero from the beginning. You make it become solid, and then you apply magnetic field, increase that, and make it melt by magnetic field rather than temperature.
Yeah, you could probably do some things if you could actually achieve these magnetic fields, right? But you can't do it on Earth, right? But an important thing which I wanted to show you here is that if you compare the slopes of these two lines, the orange one here and the slope here, you can see that the slope here becomes actually larger. So we get an increase actually in melting temperature here in these cases. And we found that these are actually entropic effects now. So we can actually calculate the entropy. So that's the entropy against temperature, and then this is the derivative of the entropy. And you can see how it goes down if you increase the magnetic field. And the explanation for that is that due to the magnetic field and this perpendicular paramagnetic bonding, even in the liquid, you will still have structure because all the bonds want to kind of stay in perpendicular to the magnetic field.
So your liquid is basically liquid crystal somehow.
Yeah. And you get new ground states here. So this is the ground state actually for neon 38 without a magnetic field, nice and spherical. And now, of course, all the bonds try to be perpendicular. So suddenly it's much better to have a state like this, where you have, again, an icosahedral structure, but kind of capped. Things like that. So you can get new phase transitions as well. And now just to end, a little bit about the combination of both. There we have two new considerations now, which become important, that we have to be able to actually describe FCC and HCP structures at the same footing, kind of. And if we use cubic simulation boxes, like everyone is normally doing, you would actually suppress HCP structures. So what we have to use is rhombic boxes instead. So we implemented our code for rhombic boxes to have ABC and ABC layering and ABAB layering at the same possibilities. And we also introduced some new changed volume moves, because the volume moves which are in the direction of the magnetic field compared to volume moves in the other directions will be different. So we just allowed for different scaling in different directions. And yeah, so what you expect now for the melting temperatures, if we have this combination now of strong magnetic fields and high pressure, what would you think happens to the melting temperature? So what we expected, it was that it goes up even higher, right? Both of them will actually increase the melting temperatures. So I also thought, okay, they will go higher. And so we did the calculations and they actually go down. So we go to this high temperature. So this is again for helium and for neon now. The melting temperatures go down. And so this is still something which we are still.
So now compared to the same temperature, but it will
the same
compared to the same magnetic field.
Yeah. So this is here for different pressures, right? And this is then without magnetic field, and this curve is with magnetic field. And at ambient pressures I showed you just before, we actually get an increase in melting temperature. And this is still the case.
If you increase the magnetic.
Yeah. But it turns around for helium around 10 gigapascals.
So what's happening?
Yeah, what's happening? That's a good question. And we are trying to figure that out at the moment. And so we look at here just at helium at 50 gigapascals now with and without magnetic fields. And what we find is that what we would have expected, that the energy change upon melting is actually increasing. Yeah. And that you would expect because you have a stabilization by this binding mechanism. But with the volume, what's happening is that the volume change upon melting actually becomes much smaller. And so this second term here, P delta V term, seems to be taking overhand, becoming more important than the delta U. And and leads to a decrease in the melting temperatures again. And it haven't figured out totally yet, but there's something interesting happening here as well. So if you would go from further away, you see that you have a sudden drop here in the volume even before the melting happens. And if you look at that, you can actually look also at the ratio of FCC and HCP atoms, which we have in our configurations, which we are sampling. And we can find that actually here you see how the FCC atoms, at the beginning, almost everything is FCC, and then it goes down and vanishes totally. So in the liquid phase here, and the HCP atoms kind of linger around 10 to 20%. But here in this case, if you have a magnetic field, suddenly you get an increase in these HCP atoms here at this point. And this is actually connected with this sharp drop in volume here. And so we think that we see here a partial solid-solid phase transition, so partially from FCC to HCP, this is something which is known that it exists in nature under high pressure, that these noble gases slowly change from FCC to HCP over a huge pressure range. So something like that might be happening there. So we find configurations which are FCC-like configurations, and we find some HCP-like configurations. And if you look at the volume as well, we see that the HCP configurations in total have smaller volume than FCC configurations. Of course, still not answers the questions why this is the case. So that's something we haven't figured out really yet. But it's clearly something like a phase transitioning happening here. So we find really these configurations really look like this, where you clearly see ABC layering. And here you have a clear AB layering. So, yeah. So there are some new phase transitions, which here seems to be happening just before melting. And with that, I'm finished. Right, so melting temperatures of noble gases increasing by high pressure and strong magnetic fields, but if we combine them, we suddenly get a decrease. And we find new solid phase transitions in these new extreme environments. And motivation, perhaps a little bit, it's possibly interesting for astronomical observations, because if noble gases become solid, you won't see them in spectral lines. And another thing is also, it will be especially interesting for magnetic white dwarfs, which are close to the Santer-Secker limit, because there you have actually a lot of helium and neon in the atmosphere. And if you have changes there in the state of, they might explode or might not explode, right?
And do you have like DFT for cross check your result?
Sorry?
You have some like independent DFT calculation to cross check your result?
Cross check. We don't have them for the magnetic field yet. For the high pressure stuff, yes, we have it. These are molecular dynamic simulations you can do. So DFT is just the electronic structure calculations. Right? But how you do the thermodynamic exploration, you can do it either with Monte Carlo or with molecular dynamics. Yeah.
Okay, good. Thank you, Elke, for this very interesting talk, which started from chemistry and ended with we had lots of questions, and we have to keep our energy. I hope our brains didn't melt so far, because we have a second seminar. But still, one or two important questions. Annika, please.
So, in the melting case,
Yeah.
when should you include also electron-phonon type interactions? Because as far as I understand, the way your simulation works, you solve the electron part first, then you have the atomic part. Yeah. So there is no interaction between them.
So I don't know yet. So this is actually, you're asking about, so what we are using is the Born-Oppenheimer approximation here always. And
now if you
I would still think that it's good, but why do you think that might break down?
Because if you increase pressure and things like that, then this electron-phonon interaction becomes, meaning then the Born-Oppenheimer doesn't work.
At some point?
Yeah.
It might be, yeah.
And this is what you use, Born-Oppenheimer, right? This is
everything at the moment is all based on Born-Oppenheimer approximation at the moment, at least, yeah. Yeah, that might be something we should be looking into it in the future.
Questions? Okay, if not, then let's thank Elke again. Thank you very much. And I remind you, we have another talk at 4 p.m. So you'll be all here by that time.